Okay, so welcome to the 39th video in the discrete structure series and a continuation of the chapter counting and discrete probability. In the last video, we covered the first topic in this chapter, and that was the basics of counting. And we looked at some numericals. In this video, we'll be looking at the pigeonhole principle. We'll look into the concept and a few problems. And then we'll be looking into what is called the generalized pigeonhole principle. And we'll do the same thing with this, dive into the core idea and then explore a few problems. And with that idea in mind, let's get started with the first topic, and we'll be looking into the concepts of the pigeonhole principle. Alright, so this principle is pretty simple, so I think we can just get started with this statement. It formally states that if k is a positive number and k plus 1 or more objects are placed into k boxes, then there is at least one box containing 2 or more of the objects. So let's dive into this definition. It mentions k boxes and k plus 1 objects. And if the number of objects are more than the number of boxes, at least 2 of the objects are forced to repeat. So let's say I have 4 objects, and this could be objects of any sort, and I have 3 given boxes, box number 1, 2, and 3. And if I have to fill these 4 objects, let me just demonstrate these as objects. The statement suggests that once I start filling these objects into these boxes, at least one of these boxes will have 2 of these objects. So if I fill one over here, and one over here, trying as hard as I can to make sure that I don't get 2 on the same box. Once I have this configuration and I have my 4th box, you see the first 3 went on one of each. And when I have this one, no matter which box I put it in, I'm going to cause that box to have 2 objects. So if I put it here, this box now has 2 objects. Now you should understand that when I have 3 boxes, I could choose to put all of the 4 objects in one box, okay? And leave nothing in these 2. And that is fine because at least one box should contain 2 or more of these objects. So having more than 2 objects does not violate the statement. And just for the sake of completion, the name pigeonhole principle comes from considering these objects as pigeons and these boxes as pigeonholes. So if 4 pigeons arrive and there are only 3 pigeonholes to accommodate them, at least 2 pigeons will end up in this box. And it turns out that this same pattern occurs in many different situations. For another example, consider that we choose a random person, let's say P1, and we want to see which day of the week his birthday falls on. Okay, so it could either be Sunday, Monday, and all the way up to a Saturday. And let's keep adding more persons. If I consider one more person P2, I know that their birthday is also going to be one of Sunday to Saturday. But the birthdays of P1 and P2 could fall on a different day. P1 could have their birthday on Monday, while this P2 could have their birthday on Thursday, for example. And the same situation keeps going until I have 7 people. Because when I'm working with 7 people, I still cannot guarantee that their birthday will repeat. Because there are 7 people and 7 possible birthdays. So P1 could have their birthday on Sunday, this one could be on Monday, Tuesday, and 7 people could have 7 different birthdays. But as soon as we introduce the 8th person, the birthday of this person should match with one of the other 7 people. Because you see, even in the worst case, these people could have separate 7 birthdays. And when I introduce the 8th person, one of them will be forced to repeat. And the same argument also applies in this example. It could coincidentally happen that all of these 8 people have their birthday on Sunday or Monday, the same day of the week. And that's kind of even better, right? Because I only need 2. So in order to challenge the pigeonhole principle, and this attitude will come in handy while problem solving later, we want the objects as equally distributed as possible. So if I start clustering them at the beginning, I already have the 2 that I need. So our thought process should be to distribute these k plus 1 objects as equally as possible. But since we have only k boxes, we are forced to have 2 in at least one box. And just in case we need a proof for this statement, we are able to offer a pretty basic proof for this by contraposition. So we are already familiar with contraposition as a proof technique. In order to prove the implication P implies Q, I want to prove it's contrapositive, not Q implies not P. So by assuming not Q, I want to prove not P. So we assume that none of the k boxes contain more than one object. And you should see this is the same as assuming not Q, because Q says there is at least one box containing more than 2 objects. And when we are saying not Q, we are saying that is false, right? None of these boxes contain more than one object. Now if none of the boxes contain more than one object, this implies that there could be at most k objects. And this should be pretty obvious. I have k boxes and none contain more than one object. So there could be at most k objects. So k is the maximum number of objects I could have in this situation. But we know that this is a contradiction. And why is that? It contradicts with my statement that assumes that there are k plus 1 or more objects. And before we dive into problems, let me show you one more thing. Imagine that I represent the assignment of pigeons and pigeonholes in a function. Okay, so I have this set A that has my 4 pigeons and this set B of pigeonholes that has only 3, for example. Now, if I want to link this pigeon to pigeonholes, I'll find that I'll be linking 2 of the inputs to the same output. Speaking in function terms, 2 of these pigeons are staying in the same pigeonhole. So what I'm really saying in functions terms is that this function is not one-to-one. So in terms of functions, we can give a statement like this. A function from a set of k plus 1 or more elements to a set of k elements cannot be one-to-one. So if I have more items in my domain than in my range, then the function cannot be one-to-one. That's all this principle is saying, and you should be able to see this is equivalent to the pigeonhole principle. Alright, now we'll move on to a few problems under the pigeonhole principle. So we'll start with a couple of basic problems, and these are more like examples than problems. In a group of 27 English words, at least 2 should start with the same letter. And you should be able to see a direct application of the pigeonhole principle here. I know that there are only 26 letters in the English alphabet. And you don't need to mention this, but just for my explanation, I'll mention these are my pigeonholes. Why? Because anytime you give me one of these 27 words, I'm going to be able to put them in one of these holes. It's going to start with one letter from A to Z. So whichever letter it starts in, I'm going to put that word into that corresponding letter hole, if that even makes sense. So my pigeonholes are representing all of the different letters from A to Z. And let's say one of these words is a kite. Then I'll assign this word along with the hole that represents K. You give me one more word like cat, I'm going to associate that with a C. And if you keep giving me words like this, anytime you give me a word with a C or a K, I have 2 words. Because eventually if you give me another word that starts with a C, that makes 2 words that start with a C. And the worst position that you can put me in is by giving 26 words that start with different letters. So you give me a word like apple that starts with A, one word with B, one word with C, one word with D, and all the way up to Z. Okay, so that will make 26 total words, and each of these words will have different starting letters because you are able to do that. But the moment you are asked to choose the 27th word, it has to repeat the letter from one of the 26 words. So we can continue. We have 27 words, and these are analogous to the pigeons. And we can see that the criteria for the pigeonhole principle has been satisfied. We have 26 letters and at least one more words than the number of letters. So if the number of letters is k, the number of words is at least k plus 1. Then we can apply the pigeonhole principle. I can say that at least 2 of these words fall under the same letter. Alright, so this was a pretty simple problem. We'll look into one kind of a real problem. And this one goes like this. So that for every integer n, there is a multiple of n that has only zeros and ones in its decimal expansion. Okay, so let's make sense of this problem. So it is basically asking me to choose any number n, any integer n. So let me call 5. Then I need to prove that for any number that I choose, I can multiply this with something so that the result only contains 1 and zeros. So in case of 5, it's pretty simple. If I do 5 times 2, I get a 10, and I can see 10 is a number only containing ones and zeros. And the question is saying no matter what number I choose, this is always possible. For another example, if I choose a number like 4, I can think of a multiple of 25. When I multiply 25, I get 100. So there exists a multiple of 25 for my 4 that results into a number containing only ones and zeros. So I hope you understand the question at least. For any number that I choose, some multiple must exist so that the result only contains 1 and zeros. And I have only shown you obvious examples here, but we are heading on to prove that this is the case for all numbers, even a prime number like 17. There is something to multiply, and the result will always be a number containing only zeros and ones. So how do we prove that something like this is possible? And how on earth does that use the pigeonhole principle? Let me make it clear by giving one more example, and this time we'll follow along the steps of the solution. So let us consider a number like 3, and our job is to prove that some number exists containing only zeros and ones, and this is a decimal number that can be obtained by multiplying this 3 with something. So in order to prove this, I'll consider 4 numbers. I'll consider the numbers 1, 1, 1, 1, 1, 1, and 1, 1, 1, 1 with 4 ones. Okay, and I choose 4 numbers because my number here is 3. If I need to prove this fact about a 7, I'll be choosing 8 different numbers. The first number will just be a 1, second number will be 11, 111, 4 ones, 5 ones, 6 ones, and as many as I need. And the reason we want to choose one more than my number 3 here is because I want to apply the pigeonhole principle. I know that when I divide any number by 3, the remainder is going to be either 0, 1 or 2. For example, if I divide a 12 by 3, the remainder is 0. If I divide a 13 by 3, 1. 14 by 3, remainder is 2. And then when I reach 15, the remainder cycles back. It is 0 again. So no matter what number I choose, when I divide it by 3, the remainder is going to be one of these 3. And therefore the big idea is, since there are 4 numbers here, if I divide each of them by 3, at least 2 of these remainders are going to be the same. And that comes because of the pigeonhole principle. So for example, if I divide this 1 by 3, the remainder is simply 1. If I divide 11 divided by 3, I know 3 times 3 is 9 and that leaves a remainder of 2. But there are only 3 remainders, so let's see where it repeats. So if I divide 111 by 3, in this case it will leave a remainder of 0. And in this case, you could calculate and check the remainder divided by 3 is going to be 1. Now when I finish this process, if there is some number that left a remainder of 0, that is the number that I'm choosing for. In this case, 111 divided by 3 is leaving a remainder of 0. So 111 is my answer. Okay? Because I can say that 3 times 37 is just equal to 111. But you should understand that I'm not guaranteed to find a 0. But what I'm guaranteed to have is that 2 of these remainders will be exactly the same. In this case, this and these are both a 1. And I can always take a difference of the larger and the smaller number. So if I take the difference of 1111 minus 1, I get a number called 1110. And this will be a number that 3 will divide. And this comes from a property of modular arithmetic. This number is leaving a remainder of 1 when divided by 3. And this number is also leaving the same remainder when dividing by 3. If I subtract these two, the remainder 1 and 1 will be cancelled out. And whatever remains will be an exact multiple of 3. So this means that even if I don't get any sequence of 1 leave a remainder of 0, I'm going to get at least 2 numbers that leave the same remainder. And the difference of those numbers is going to be divisible by my original number 3. And now let's get back to our example of 5. When I have 5, I want to consider 6 numbers, starting with a single 1, then 2 ones, 3, all the way up to 6 ones. And there are 6 numbers here and only 5 possible remainders because the remainder are going to be between 0 and 4. So if I look into the remainders, it's easy. Dividing by 5, all of these numbers will leave a remainder of 1, right? Because this is 1111. 5 will go up to 1110 and leave the remainder of 1. And what do I need for my proof? I want at least 2 of these to be the same. Now multiple of them are same. In fact, all of them are same. But again, repeating for the 100th time, I only want 2 of these to be the same. Any 2 of these can be the same. And that is guaranteed by the pigeonhole principle. And I'll take 2 of them that are the same. So let me take any 2, 1111 and 111. If I take a difference of these numbers, I get 1000, which is 1000, and a multiple of 5. Therefore, we can show this process for any number n and eventually come up with a number that only contains 0 and 1, which will be a multiple of the given number. So let's do this formally now. So we'll say that given integer n, consider the following sets with n plus 1 elements. And I'm going to call this set as, and it will start with a single 1, 2 ones, 3 ones, all the way. Okay? Where the last term is just going to be 1, 1, 1, 1, 1, n plus 1 times. So it is the same as doing this. For a number like 5, I want to start with a single 1, 2 ones and reach 6 ones. For any integer n, I want to start with 1, 11 and head up that way until I have n plus 1 ones in the final term. Now we can say that by the pigeonhole principle, at least 2 of these numbers will leave the same remainder when divided by n. And why is this? Because there are only n possible remainders. And those remainders are from 0 to n minus 1. So in case of 5, my remainders are going to be between 0 and 4. So the total number of possible remainders is 5. So there are only n possible remainders, but there are n plus 1 numbers that I'm dividing and taking the remainder from. So at least 2 of these will give the same remainder, and that's what we have stated here. And now we could say let these numbers be a and b. And finally, I could write the conclusion. The difference, a minus b, will only contain 0 and 1s. And why is that? Because all of my numbers are just 1s. When I subtract them, it's just going to give zeros. And for the digits that are already there, it's just going to give a 1. So assuming that I have my bigger number on top and my smaller number on the bottom, all of those digits corresponding to the smaller number are going to be zeros. And all of the remaining digits are going to be 1. So I can say that this result is always going to contain zeros and 1s. That's what we're saying here. The difference a minus b will only contain 0 and 1. Moreover, we are able to observe that a and b leave the same remainder when divided by n. And that is the same as saying A is congruent to B mod n. And you could mention this is because A and B are leaving the same remainder when divided by n. And from this, we are able to say that n divides A minus B. So we have finally found our number A minus B, which only contains 0 and 1s and is also a multiple of n. So this will arguably be the toughest problem that you might get on Pigeonhole Principle. And to be honest, looking into this problem and generating this idea real time will almost be impossible. But if you have seen this problem and understand this approach, the solution should be really intuitive and easy to understand. And with that said, we'll move on to the second topic of our day, and that will be the generalized pigeonhole principle. And let's make this concept clear as well. This is just an expansion of the pigeonhole principle. So in our earlier example, we talked about 4 pigeons and 3 pigeonholes. And in this configuration, we have established that at least one of these pigeonholes will contain 2 or more pigeons. Right? Because if I distribute them 1 on 1, this accommodates for 3 pigeons and I'm forced to put the 4th pigeon in one of these holes. And that will cause one of these holes to contain 2 pigeons. So we are really saying that if we have k plus 1 or more pigeons and only k pigeonholes, at least one box will have at least 2 pigeons, and 2 is the main number that you want to understand. I want you to think about it in this way. What does it take to guarantee that 3 pigeons will be on the same pigeonhole? Is there a number of pigeons that will guarantee that I have 3 pigeons on the same pigeonhole? And here's the thought process. Let me consider the 3 pigeonholes again. And this time I want to guarantee that there are at least 3 pigeons in one of these holes. Okay, I worked for 2, but this time I want to guarantee 3. So how many pigeons do I really need to do that? So let's have 3 pigeons. I'm not even forced to have 2 like we saw about. I could put them in one of these holes each, and none of these even have 2. And we understand that the moment I introduce one more pigeon, one of these holes will have 2 pigeons. So let's say I introduce the 4th pigeon. I have 2. But the thing is, even if I have 5 pigeons, I could still have 2, 2 and 1. If I have 6 pigeons, I could have 2, 2 and 2. Okay? So this is for 6 pigeons. But the moment I introduce my 7th pigeon, it has to again go into one of these 3 pigeon holes. That means this time I'm able to guarantee that at least one of these holes contain at least 3 pigeons. Because the 7th pigeon, if I put it here, that makes it 3. So here's the big takeaway. If I have 3 pigeonholes, let's keep this constant. If I want to guarantee at least 2, the number is going to be 3 into 1 plus 1. Because this means 1 pigeon in each of the 3 boxes, and I need 1 more pigeon to guarantee that 2 of them will repeat. Okay, so 3 into 1 means 1, 1, 1. Okay, and if I have 1 more extra, that will cause it to repeat. In this case also it is quite similar. I have 3 pigeonholes, and if I have only 3 into 2 is equals to 6 pigeons, I'm not able to guarantee that 3 of them will be on the same hole. Because you see 2 pigeons are placed in each of the 3 holes. But if I have 1 more than that, 3 into 2 plus 1, then I'm able to guarantee what I want, that 3 pigeons will be on the same pigeonhole. So with that, I think we're ready to make sense of the statement. If n objects are placed into k boxes, then there is at least one box containing at least the ceiling of n by k objects. And let's look into this statement in relation to this example. I have n pigeons and k pigeonholes, right? N objects and k boxes. And in this statement, my value of k is just 3. That is my denominator. And hopefully this ceiling value will be the number of objects that I'm guaranteed to have. In this case 3, in this case it's gonna be 2. And we know that in order to guarantee 2, we need at least 4 pigeons. If I have any number of pigeons from 1 to 3, you should be able to see that this value will always be greater than 0 and less than 1. Because if I choose 1, I get 1 by 3. And if I choose 2, I get 2 by 3. And if I choose 3, I just get a 1. And when I take a ceiling of this value, I'm getting a 1. So what is this 1 saying? Well, it is saying if you have 1 to 3 pigeons, you can only guarantee 1 pigeon in each pigeonhole. And that is correct. If I have only 3 pigeons, I could put them 1, 2 and 3 like so. But the moment I choose 4, I get a ceiling of 4 by 3. Okay. And this is just going to be 2 because 4 by 3 is 1 point something. And if I take the ceiling of that, this is going to give me 2. So that means if I have 4 pigeons, 2 of them will be guaranteed to be on the same hole. And what do you think will happen for 5? 5 by 3? You should be able to see that 5 by 3 is still a number between 1 and 2. And even if I choose 1 more, if I choose 6, I get a 6 by 3. And this will still be a 2. So up to 6 pigeons, I can still only guarantee 2. Because 1, 2, 3, 4, 5, 6. Now in order to guarantee 3, I need 7, right? From this example, 3, 4, 5 and 6, 7. And if I plug 7 into this formula, I get a floor of 7 by 3. And this time it is 2 times something. And if I take a ceiling of 2 times something, I get a 3. So in some sense, the generalized pigeonhole principle is telling us more than the normal pigeonhole principle. Because even if I consider this problem for the normal pigeonhole principle, it would just guarantee 2. And that would be correct because I have at least 2 pigeons in one of these holes. But then the generalized pigeonhole principle comes up and says, that's not the best we can do. We cannot just guarantee 2, but we can guarantee 3 or 4 or 5, any number of pigeons that we want by considering a sufficient number of pigeons to begin with. And if we go back to our birthday example quickly, we said that if there were 8 people, 2 of them will have the same birthday on the same day of the week. And how many people do you need to guarantee that there are at least 3 birthdays common? See, when I have 14 people, this could potentially be the worst case because 2 could be from Sunday, 2 could be from Monday, 2 for Tuesday, and all the way to for Saturday. So that would make 14 distinct people. But still we are not able to guarantee that 3 of them will have the same day. But as soon as I introduce my 15th person, I can guarantee that 3 people in that group will have the same day of the week as their birthday. Because even the most unlikely distribution causes that to happen. Alright, next we'll dive into a couple of problems from the generalized pigeonhole principle. And before looking into the problem, let us just quickly look into the proof. I'll just put the statement here. Alright, so the statement is basically if these two are true, then this is true. And we'll use the same proof technique of contraposition to prove P implies Q. We'll start by assuming not Q and then use that to prove not P. So to begin this, we can assume that not Q is true, that none of the K boxes contain more than this number of objects. So we'll assume that none of the K boxes has more than the ceiling of n by K minus 1 objects. And why do I need the minus 1 here? Because I want to negate something like at least 5. If you want to say that at least 5 is false, you have to say at most 4. Okay, because at least 5 will be 5, 6, 7 or any number that is greater than 5 because it is at least 5. And if it is not true, the number should be less than 5. So it can be at most 4. In our case, the ceiling of n by k or more objects are guaranteed. And if I want to assume that false, I need to assume that no boxes has more than this quantity minus 1 objects. Now this means the number of objects is definitely less than k times this value. And writing this is the same as writing this. None of the k boxes has more than these many objects. If I multiply the number of boxes with the number of objects, I get k times this value. Therefore, the total number of objects should be strictly less than the number of boxes times whatever this number is. And then we'll apply a small trick here. We'll write this as n by k plus 1. And what is the relationship between this value, the ceiling of n by k and n by k plus 1? So let's look at a couple of examples. So if I have n is equals to 5 and k is equals to 3. And this will apply in any case where this divided by this is not an exact number. Okay, so 5 divided by 3 is 1 point something. And if I take a ceiling of this value, I get a 2. So the ceiling of n by k is just equal to 2. But then what is n by k plus 1 in this case? So 5 divided by 3, if I just do n by k, that will just give me 1.67. And then if I add this one, I get a 2.67. Okay, so when I take n by k plus 1, it is always going to be greater than the ceiling of n by k. So you could take other examples like 6. 6 by 3 is just 2. The ceiling of 2 is also 2. But if I take 6 by 3 plus 1, that is again going to give me 3. So for any numbers n by k, this number n by k plus 1 will always be greater than this ceiling. So if I just replace this with this value and leave the other things the same, I can say that this number is definitely greater. Okay, so the total number of objects being less than this is most definitely less than this, is what we're saying here. And with a little bit of simplification, I can say this is just k times n by k, and this will just be equal to n. So what did we actually prove? We proved that the number of objects is less than n. So we proved that the number of objects is less than n, which is a contradiction. Because the fact that I have n objects is given by the question. I cannot have a number of objects that is less than n. And this contradiction only occurred by assuming this. So this assumption was false. And this assumption was false means that at least one box contains at least the ceiling of n by k objects. So we have effectively proven that anytime the consequent q is false, the premise p must also be false. We did that by contraposition, and that completes the proof. Alright, next we get into a couple of problems for the generalized pigeonhole principle, and then we'll close the topic for today. So let me put this problem here. How many cards must be selected from a deck of 52 cards to guarantee that? And then the question provides two cases. The first case mentions that at least 3 cards of the same suit are chosen. And in the second case, we'll ask at least 3 hearts are chosen. Okay, now in this problem, we have 4 total boxes. Why? Because there are 4 total suits: clubs, diamonds, spades, and hearts. And each time I pick a card, it must fall on one of these 4 suits. So think about it. If I have 4 cards, it could be 1 spade, 1 club, 1 heart, and 1 diamond. But as soon as I have 5 cards, I'm forced to have 2 of them from the same suit, because either spade, heart, diamond, or club will repeat after the 5th card has been introduced. But guaranteeing at least 2 is not enough for me in this case. I need to guarantee at least 3 of the same suit. And if we continue our train of thought, if I have up to 8 cards, I still cannot guarantee that 3 of them will be on the same suit, because 8 means 2 diamonds, 2 spades, 2 clubs, and 2 hearts. And you should understand, it's not always going to be 2 of each. But I need a criteria to be able to guarantee that 3 of them will be in the same suit. So to make it as hard for myself, I'm saying that even though I have 8 different cards, I cannot still guarantee that 3 of them are of the same suit. But in practice, choosing 8 cards make it extremely likely to get 3 of the same suit. But can it absolutely mathematically be guaranteed? No, because 8 cards can still accommodate 2 of each suit. So in order to guarantee that 3 of them will fall on the same suit, I need 1 more card, and that will be equal to 9. So 9 is our answer. The moment we have 9 cards, we guarantee that 3 of them will be on the same suit. But what is the formal way to answer this? So we say that let n cards are necessary. We know that there are a total of 4 suits, and we want 3 of the same suit. That means by my generalized pigeonhole principle, I can borrow the expression from earlier. The ceiling of n by 4 is going to be greater than or equal to 3. Okay, so n pigeons, 4 pigeonholes, and I'm going to guarantee at least 3 pigeons per pigeonhole. And from this point, we just proceed with our intuition. The smallest n to satisfy the value will be given by 4 times 3 minus 1 plus 1. Okay, so this is going to be the pattern. You want to multiply this 4 with 1 less than the number that you are trying to guarantee. So that gives me 3 minus 1 and plus 1. So what we're effectively doing here is saying 4 times 2 plus 1. And I want to highlight again the importance of understanding this rather than remembering it. We're just saying that we want to guarantee 3. And in order to guarantee 3, I must fill all of the 4 boxes tightly with 2 objects. And once I fill these 4 boxes tightly with 2 objects on each one, the next object to be introduced will cause 3 objects to be on the same box. So when I'm taking 3 minus 1 and multiplying by 4, I'm just packing all of the 4 boxes with the maximum number that I can, and that is 2. And once I've done this optimal packing of 4 times 2, adding 1 more will cause 3 objects in the box as we talked about. So I think the big win is to think about this in logical terms. But even if you don't want to for some reason, if you have n by k and you want to guarantee some number, you want to multiply the denominator with that number minus 1 and then add a 1. And in this case, this will just be equal to 9 cards. So I hope this is clear, and we'll move on to the next side of the problem. Here it suggests that at least 3 hearts are chosen. Okay, so 3 of the same suit here. But now any suit will not do. I have to have a heart. And the reason the second problem is here is because it doesn't even use the generalized principle, but it still uses the core idea of the distribution that we talked about earlier. So what is the maximum number of cards that you can choose while still guaranteeing that there are no 3 hearts? See, I know that even if I choose 39 different cards, okay, there is a random chance, a very low chance, but there is a chance that this 39 could be composed of 13 spades, 13 diamonds, and 13 clubs. So that means even if I have 39 cards, I cannot even guarantee a single heart. But what happens when I have 40? Now with 40 cards, I'm guaranteed to have at least 1 heart. Because even if you choose this worst case for me, even if all the 39 formally chosen cards were not hearts, the 40th chosen card causes the 1 heart to follow. And again, we are not saying that 40 cards will contain exactly 1 heart. That is ridiculous. We are just saying that if you choose 40, at least 1 heart is guaranteed. But I want to be able to guarantee 3 hearts. Therefore, I need to choose 42. Okay, because 40 guarantees 1 heart, 41 will guarantee 2 hearts, and 42 will guarantee 3 hearts. So this thought process of this worst distribution, and I also talked about this in the beginning of the video, will be very helpful in problem solving. So my reasoning here is exactly the pattern that we'll use to answer this part. We'll say even with 39 cards, no heart is guaranteed, as it could just be 13 of each of the other suites. But if we introduce 3 more cards, from the worst case, we are forced to introduce 3 hearts. Therefore, the minimum number of cards to guarantee 3 hearts is just going to be 39 plus 3. And this is going to be equal to 42. So I hope this problem makes sense. It demonstrates 2 important aspects. One, how to use the pigeonhole principle. And second, how to generalize the concept for distributions in general to compute numbers and find solutions like these. Alright, we'll look into the last problem of the day from pigeonhole principle. I'll put the problem here again. And this problem says during a month with 30 days, a team plays at least 1 game a day, but not more than 45 total. Prove that there must be a period of some number of consecutive days during which the team played exactly 14 games. So what is this question asking? So we have a month of 30 different days. So day 1, day 2, all the way up to day 30. And this team plays at least 1 game on each of these days. Okay, so there is not a single day where there has not been a game. So 1 game here, 1 game here. I'm not saying exactly 1, but at least 1. And it is also saying that they did not play more than 45 games. It has not told me exactly 45. So for simplicity, we'll just assume that they played 30 games. Now we need to prove that there must be a period of some number of days, consecutive days, during which the team played exactly 14 games. And so it's important to understand it does not mean that 14 games should be played on a single day, but there should be at least some group of consecutive days for which the total number of games will just be 14. And this sounds obvious, but let me tell you, it really is not. In this particular example, it's easy to see. If I take days number 1 to 14, 1 game has happened on each day. That means in this consecutive span of 14 days, exactly 14 games were played. And let me give you a few counter examples to make it even more clear. So let's say on the very first day, 10 different games were played. We are allowed to assume this because it only says at least 1 game must be played. And we must also be aware not to exceed 45 by total. And let's say on the second day, we play 3 games. That means we have played 13 games total. Now if we play 1 game on the third day, now in these 3 days, we played exactly 14 games. But we are not forced to do that. We could just say we played 2 games on day number 3. And now in these 3 consecutive days, there is no 14. There is just 10 plus 3, 13 plus 2 is equals to 15. So I couldn't find it. But the problem says that I will be able to find it. I have not completed this process yet. So I just played 10 plus 3 is equals to 13 and 13 plus 2 is equals to 15 games. There are still 27 days remaining from 4 to 30. And each of these will have to have at least 1 games. That has to be guaranteed. And what we need to prove is that eventually there will be at least a group that adds up to 14. Okay, so there will be a list of consecutive days in which the total number of games will be exactly 14. And how can we say that that can be guaranteed given this situation? So let me show you the solution and we'll follow along it. So let's say the sequence, and we'll say the sequence A1, A2, A3, and it goes all the way up to A30 be the cumulative number of games played till the respective date. And before I move on, you should understand we are assuming cumulative number of games. Okay, so in this case, in the first day I played 10 games. That means A1 is equals to 10. And in the second day I played 3 games. But I don't want to consider 3 because I want to consider the cumulative value. So for A2, I'll say it is equal to 13. Okay, so 10 plus 3. And on the third day we played 2 games. Therefore A3 would be 2 more than 13, would be equal to 15. So I want you to understand that these terms A1, A2, A3 are not the individual number of games played each day, but rather the total number of games played until that day. Hope that is clear. And next we want to capture a couple of properties of this sequence. One, it is strictly increasing. And that is because I'm taking a cumulative sum. We know that at least 1 game is played on each day, right? So A2 will be greater than A1 by at least 1. And even if only 1 game was played on the second day, this A2 number would be 2 because that is the total number of games. If 2 more games were played on the third day, my A3 would be equal to 4. That is 2 plus this former value. And since 1 game is played on every day, I can say that this sequence is strictly increasing. Okay, so no 2 numbers are same and they are always increasing. And the second thing that I can say is that AJ is less than or equal to 45 for all j between 1 and 30. So what are we saying here? Since 45 is the maximum number of games that we could have played, every number in this sequence cannot be more than 45. Because if you happen to play all the 45 games, A30 will just be equal to 45. Because this will accumulate all the games that has been played in the past. And the maximum number this could be is just gonna be equal to 45. And this property being true for the last number is definitely true for all other numbers. So for any j that I choose between 1 and 30, the respective a is gonna be less than or equal to 45. Now we consider another sequence. This time adding a fixed value of 14 to each of the existing terms. And this will result in the sequence. And I'll just have a1 plus 14 as my first term, a2 plus 14 as my second term, and so on. Alright, let me get a little bit of space on this side. Now the first thing that we want to observe is that this sequence is also strictly increasing. Because if the original sequence is strictly increasing, if I add 14 to each term, the resulting sequence will also be strictly increasing. So for this sequence, we can also make the same observation. It is strictly increasing, and this one will change slightly because I added 14. I'll be able to write my original number aj was always less than 45. So when I add 14, it's going to be less than 45 plus 14, and that's going to be 59. So I'll be able to say that aj plus 14 is going to be less than or equal to 59. Okay, and that is 14 added to this 45. And if you look at it carefully, we are just saying 1 is less than aj, less than 45 in this case. The number of games played for any random day should be between 1 and 45. Because one game has to be played on each day, so this will make it true even for the very first day. And this 45 is my upper limit. By the end of the 38th day, I cannot exceed these number of games. But if I'm choosing to add 14, I need to add it not just to this 45, but also to the starting limit. So if my original number is between 1 and 45, when I add 14, it is going to be between 15 and 59. And this fact will also be true for all j between 1 and 30. Now here's the big thing. We consider both of these sequences together. Considering both sequences together, how many total numbers do we have in our combined sequence? In my first sequence, I have 30 terms, a1 to a30. In my second sequence, I also have 30 terms, a1 plus 14 all the way to a30 plus 14. So the total number of terms in both of these two sequences combined is 60. But we know that all of these numbers are less than 59, because even after adding 14, I can tell that the maximum is going to be less than 59 by this. But all of these numbers are less than 59. So you have total 60 numbers in your sequence, but all of them are less than 59. That means at least two of those numbers should be exactly the same, because if none of them are equal, all 60 numbers cannot be less than 59. And this is a direct consequence of our pigeonhole principle, trying to put 60 pigeons in 59 pigeonholes. Therefore, at least two of these numbers should be equal. Now again, we ask a big question. Can these two equal numbers come from the same set? We know that there are no equal numbers in each set because they are strictly increasing, right? Because no two numbers in this first 30 are equal. And we also know that no two numbers in the second 30 are equal. So the fact that we found that two numbers were equal means that one of the numbers must be from this first list and one of the numbers must be from the second list. So we'll continue. We'll say moreover, these two numbers belong in different sequences. And the reason is both of them are strictly increasing. That means none of the numbers in the individual sequences are equal. And I can take advantage of this equality now. So let me choose any representative number from the first sequence and I'll just call it AI. And any representative number from the second sequence will just be equal to AJ plus 14. And we know that these numbers are equal. We don't know exactly which numbers are equal, but we know that there exists at least one I and one J, so that if I choose a term from the first sequence and J from the second sequence, these numbers are going to be equal. And that follows from this reasoning. And what does this really mean? When we reached the ith day, the number of games played were 14 more than the number of games played on the jth day. So we'll say exactly that. So from this point onwards, from the expression we can say, we can conclude that exactly 14 games were played between the ith and the jth day. So yeah, this is quite a tricky problem, I agree. And I also agree that there's no way to get this right unless you have seen the problem first. I'm not saying it's impossible, but being able to think through this reasoning process in the exam will be near impossible. And there are a few other questions which can only be solved by knowing the exact technique. Unfortunately, I do not have time to cover all of those questions in this lecture. So I invite you guys to follow the textbook from Kenneth and Rosen and to see all of the potential problems, just so you don't miss anything. But with that said, I'll complete my part of the pigeonhole principle, and that will be all the discussion that we'll have for today. From the next video, we'll be starting the topics of permutations and combinations. So I'll see you guys tomorrow with the next one. Have a good day and bye.